Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's see how we did on our homework for last night. First problem, Daniel needed to paint his patio, so he made a scale drawing of it. Here is his drawing, and his drawing is on, it's 4 inches by 7 inches. He knows that the width of the patio is 10 feet, but the scale drawing is in inches. Okay. I'm a little bit annoyed by the premise of this. How's he making a scale drawing if he doesn't know this dimension of the patio? But whatever. Let's just go with it. So find the length of the patio in feet. So a lot of times people, when they look at this, students think that they have to change this to a number of inches or this to a fraction of a foot. Turns out for this proportional reasoning, it doesn't make any difference at all. We're just focusing on the numbers, not on the unit of measurement. So if we write the unit of measurements for, or the dimensions of the patio is 10 over x, and the 4 corresponds with the 10, then we will write this as 4 over 7. So we know that x is more than 10. How much more? Well, you could think of it in terms of a scale factor or a giant 1. What do you multiply times 4 to give you 10? And that would be 2.5. So 7 times 2.5 will give you x. Or you could just cross multiply and get 4x's is equal to 70. So whatever 70 divided by 4 is, that's going to be your answer. Now find the area of the patio. So if we know this is 17.5, then to find the area, you're going to multiply base times height. So 10 times 17.5 is 175. Now 1 can of paint covers 125 square feet. So 1 can of paint is not going to be enough. How many cans of paint will Daniel need to buy? Well, that's pretty straightforward. You don't need to do proportional reasoning for this because you're not going to buy a fraction of a can. You're either going to buy 1 can or 2 can or 3 cans. So 2 cans will cover 250 square feet, which is plenty. So we're just going to not bother doing anything other than mental math and just say that's 2 cans. Juan found that 20 pencils weighed 12 ounces. How much would 50 pencils weigh? Okay, so you can set this up for a proportional reasoning, cross multiply, or look for a giant 1. I guess that would be 2.5 that you would multiply times 12 ounces. And I'll go ahead and show that. If you multiply 20 times 2, it's 40. 20 times 2.5 is going to be 50. So whatever 12 times 2.5 is, that's going to be your x. Other students might have decided to do this. They would say, well, if it's 20 pencils for 12 ounces, how many pencils would it be per ounce? You could do it that way and then use that unit rate to figure out that it's going to be 30 ounces. But I think this is the best way. So 12 times 2.5 is 30. So that is going to be the weight of 50 pencils. All right, a lot of stuff going on here. First thing we need to do is, I guess we need to solve for x, right? They didn't ask us to determine what this angle was or that angle is, but we could figure it out. We know that these two angles combined form a right angle. That means that 6x plus 4x plus 10 has to equal 90. So by the time you go through the process of combining like terms, 10x's, take away 10 from each side. So 10x's equals 80, so 1x has to equal 8. Now let's prove that that's correct by figuring out if x is equal to 8, then this is a 48-degree angle, and this one would have to be, what is that, 32. This would have to be a 42-degree angle. Add those together. Do they add up to 90 degrees? Yes, they do. So that's our proof. That's our check to make sure that x had to be equal to 8. What do these two angles have to add up to? Well, they form a straight line, so they're supplementary angles, so they add up to 180 degrees. So 5x plus 13 plus 3x plus 7 equals 180. Combine like terms. 13 and 7 makes 20, so you subtract 20 from 180, so that means that 8x's has to equal 160, which means that the x has to be equal to 20. So does that work out? Is 100 plus 13 113? And 60 plus 7 is 67. Add these two together. Is 67 plus 113 180? Yes, it is. So we've got this correct. Triangle sum theorem tells us that all three angles of any triangle have to add up to 180 degrees. So combine like terms, you end up with, what is that, 7x's plus 3540 equals 180. So you take away the 40, so 7x's equals 140. 140 divided by 7 is 20. So let's see what this one would be. 65 degrees. This would be 40, 58 degrees. This one would be 40, 57 degrees. So 65 plus 58 plus 57, does that equal 180? I bet it does. That's 1520. 10 and 8 makes 180. Yes, it does. So x has to be equal to 20. And in this one, triangle sum theorem again, we know that all three of them add up to 180. So you know that these two would have to add up to 90. So you could say x has to be whatever 90 minus 30 is. So x has to be 60. And 60, 30, 90 adds up to 180. So got that one correct as well. All right, this is getting you ready for chapter 10 when we're going to start working with volume. Surface area and volume. Surface area is the total area of all the sides of a shape, of a solid figure, where the volume is the number of cubic units you can fit into a shape. So I'm going to start with the volume first. One of the things, spatial understanding is knowing that there might be some cubes in here that you can't see. For instance, I see this one, 1, 2, 3, 4, 5, 6, 7, 8. This one is 9. You know there's another one tucked in under there. This guy can't be just floating in air. It's got to be sitting on another cube. So it's going to be a total of 10. And last year when we were working through volume with the birthday, was it the birthday cake or the birthday dessert that was in the shape of an L? We took how many, what was the area of the base? So the area here is 1, 2, 3, 4, 5. And so the first layer has got to be 5 cubic units. And how many layers do we have here? We've got 2 layers, so 2 times 5 equals 10 total cubic units. So hopefully you remembered that from 7th grade, or you were just able to logic your way to an answer. Now, finding the surface area. This is a little tricky with these solid figures. We've got to keep track of all the different sides. So I'm going to make a list. You've got the top, right? Here are all the tops. And then you've got a bottom, which is pretty much going to be the same as the top. It's just the underneath portion of this. So the top and the bottom are going to match. Let's just go ahead and figure out how many square units there are there. 1, 2, 3, 4, 5. So the top will have 5, and the bottom will have 5. Now let's look at the right side. The right side has 1, 2, and then 3, 4. So if you were standing over here looking at it from this direction, you would see 1, 2, 3, 4 squares. And so if you went over, let's take a walk. Okay, on this side, you can't see any of those squares, but this person does have a view of 1, 2 on the top and 2 on the bottom. So there would be 4 square units visible to this person right here. Then you go to the front, and that's the vantage point we can see. We can see 1, 2, 3, 4, 5, 6, 7, 8 on the front. And this dude, let's move you around to the back. And from here, what would you be able to see? You'd be able to see 2 rows of 4. So 1, 2, 3, 4, 5, 6, 7, 8 on the back as well. So to find the surface area, you have to take all of those dimensions of your solid figure and figure out what the area of each side is. And so we add these together, that's 10. Add those together, that's 8. So 3 eighths is going to make a total of 24 plus 10 is 34 square units is the total surface area of this solid figure. We will get more into this when we get into chapter 10. Right now, we're just reviewing some of the basics that we've learned from 6th and 7th grade. Speaking of the basics, when we are working with solid figures in chapter 10, we're also going to be learning about cones and spheres. and cylinders. And those three types of solid figures all have one thing in common. They all contain circles. So we need to know how to find the circles, the area of the circles, and the circumference of the circles. But for this exercise, we're only focusing on area. So this is the formula to find the area of any circle. You take the radius and square it, and you multiply it times pi. I believe at the beginning of chapter 10, maybe the second or third lesson in there, we are going to review why we do this particular formula for the area of any circle. Unfortunately, oh yeah, I guess I have a video. I could show it on the video. Good. Okay. So what do we have here? This is the radius. This is the diameter. So we need to know that the radius is half the length of any diameter, and a diameter is 2 times whatever the radius is, right? So if we put it in the center point there, this radius would be 30 and this radius would be 30 because the total diameter is 60. That's important because this formula requires the radius. So here it says the radius is 8, so we're going to square the radius. So area is equal to pi times whatever 8 squared is. So that means we're going to take 64 and multiply it times pi. Now, you may have been taught that pi is rounded off to a number that is 3.14, but technically pi is, where are you, pi? There's the pi button on my scientific calculator. Pi is this really long irrational number that just keeps going on forever and ever and ever with no repeating pattern to the decimals. So we just rounded off to the 2 decimal places, 3.14. But since you have a calculator, a scientific calculator most likely has a pi button. I almost guarantee it, but not entirely. Most scientific calculators will have that. So just use that button. So when we take 64 times pi, we're just going to take 64 and then multiply it times, push the pi button. There's pi, hit equal, and that's going to be your answer in this 201.06. I'll just round it off to 201.06. And that's the number, since it's area, the number of square centimeters that you could fit inside that circle. Now, think about it. If we were to create a bunch of squares in here, you'd have a bunch of complete squares, but also a lot of partial squares. So it's not like a rectangle or a square where you can actually create the model and count up all the squares. It's not like this right here where you can count the squares. You have to use the formula, and you'll want to use your calculator for that. Here, once again, our radius was 30, so the area of this circle is going to be pi times, that's a pi symbol, by the way, times 30 squared. 30 squared is 900, so take 900, no, yes, times pi, and you get this, which we'll just round to either 0.4 or 0.43. I decided to round it to 2,827.43 square centimeters. That would fill up that circle. And our last problem, I believe, yes, it's our last problem, is just a review of scientific notation. Remember, a number like this, you don't really need to write it in scientific notation. We understand what 49.63 is. It's a little bit less than 50. But when you start getting into these really long decimal numbers and these really large numbers, even though 3,120,000,000 isn't that hard to comprehend, this is the reason why we have scientific notation. So to put this into scientific notation, you underline the very first non-zero digit in each one of these numbers. You then identify what place is that number in. That's the tens place, so that would be 10 to the first power. This is the 1, 2, 3, 4, 5, 6, 7th decimal place, so that's 10 to the negative 7th. And this is the billions place, which happens to be 10 to the 9th power, because 1 billion has 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. So we're going to take these leading digits and we're going to rewrite this as a number between 1 and 10. So 49.63 becomes 4.963, and then that gets multiplied times 10, right? Because 10 times 4 is 40, 10 times 4.9 is 49. So this is technically 10 to the first power. So we'll just put the number 1 there. Even though some of you may have chosen not to put that 1 in there, that would still be correct. But with these, that's a number between 1 and 10, so we're going to write that in, times 10 to the 7th, negative 7th, and here this becomes 3.12 times 1 billion in a power of 10. So hopefully you remember that from our previous chapter. I think that was chapter 8. You know, when you get into science classes, chemistry classes, you'll probably end up using scientific notation in those classes in high school and college. All right, great job, hopefully, on your homework, and I will see you next time. Bye.
Hey, feeling good, like I should. When in dark, I walk around the neighborhood.